As my introductory example, I picked the example of an auction. So the idea is somebody wants to auction an NFT, a non-fungible token, that is a native token on Cardano that only exists exactly once. And the NFT itself can represent some digital art or maybe also some real world asset. And the owner of the token wants to auction it away. And the idea is that this auction is parameterized by the owner of the token and the token itself, then a minimal bid, so no bid below that minimum will be accepted, and a deadline, so all the bids have to arrive before the deadline. So let's say that Alice has an NFT and wants to auction it. So she creates a UTXO at the script output, where the script is the auction script. We will look at the code later, but first I just want to explain the idea in the UTXO model. And the value of that UTXO is just the NFT, and the datum at the moment is nothing. Later it will be the highest bidder and the highest bid. But right now there hasn't been a bid, so it's nothing. In the real blockchain, you can't have a UTXO that just contains native tokens. They always have to be accompanied by some ADA, but I'm ignoring this for simplicity here. Now let's say that Bob wants to bid 100 ADA. Maybe that's the minimal bid. So in order to do this, Bob creates a transaction with 2 inputs and 1 output. And the first input is the auction UTXO. The second input is Bob's bid of 100 ADA. And the output is again at the auction script, but now the value and the datum has changed. So before the datum was just nothing because there hadn't been a bid yet. Now it's just Bob and 100. So it records the highest bidder, Bob, and how high the bid was, 100. The value has changed because now there is not only the NFT contained in this UTXO, but also the 100 ADA bid. And as a redeemer, in order to unlock the original auction UTXO, we use something called bid. So that's just an algebraic data type. There will be other values as well, but one of those is bid. And the script, the auction script, will check that all the conditions are satisfied. So in this case, the script has to check that the bid happens before the deadline, that the bid is high enough, higher than the minimal bid, and that the correct inputs and outputs are there. So the auction is an input and also an output that again contains the NFT and contains the correct highest bid in addition to that, and that the datum is updated correctly. Next, let's assume that Charlie wants to outbid Bob and bid 200 ADA. So Charlie will create another transaction, this time one with 2 inputs and 2 outputs. So as in the first case, the 2 inputs are Charlie's bid, the 200 ADA, and the auction UTXO. And one of the outputs is the updated auction UTXO. So when I say updated, recall that I earlier said nothing ever changes. So the old auction UTXO is consumed, is spent, and a new one is created. But it has this feel of updating the state of the auction UTXO. Anyway, so that gets updated. So instead of NFT and 100 ADA, it will now contain NFT and 200 ADA, the newest highest bid. And also the datum will reflect that now the highest bidder is Charlie and the highest bid is 200. And there will be an additional output, namely Bob will get his bid back. And that's also the reason, one of the reasons we have to recall the highest bidder and the highest bid so that we know who will get the old highest bid back. And in this case, we again use the bid redeemer, but now the script has to check as before that the deadline has not been reached, It has to check that the new highest bit is actually higher than the old highest bit. It has to check that the new auction UTXO is correctly updated. And it also has to make sure that the original highest bidder, Bob in this case, gets his bid back. Finally, let's assume that there won't be another bid. So once the deadline has been reached, the auction can be closed. In order to do that, somebody has to create yet another transaction. That could be Alice, who wants her bid, or it could also be Charlie, who wants the NFT. It doesn't matter. It can be anybody, but those two actually have an incentive to create this transaction. So this transaction will have one input, just the auction UTXO, with redeemer close, not bid in this case, and two outputs. And one of the outputs is the highest bidder, Charlie, and he gets the NFT. He won the auction, so he gets what was auctioned away. And Alice, the owner of the auction, the original owner of the NFT, she gets the highest bid. And that closes the auction and finishes this scenario. And the script in the close case has to check that the deadline has been reached and that the highest bidder gets the NFT and that the auction owner gets the highest bid. There's one more scenario for us to consider, namely that nobody made any bid. So Alice starts the auction, but then nobody creates a bid. And in that case, there must be a mechanism for Alice to retrieve her NFT. So for that, she creates a transaction again with the close redeemer. But now, because there is no bidder, the NFT doesn't go to the highest bidder because there is no highest bidder, but simply goes back to herself. So the logic in this case, if there is no highest bidder, is slightly different for the close redeemer. It must check that the NFT goes back to Alice. Actually, it doesn't have to check anything because, I mean, this will be triggered by Alice. Alice will create this transaction, and of course, she could send the NFT wherever she wants to. Let's have a brief look at the code, but don't worry, I don't expect you to understand it at this point. So an important thing to realize about Plutus is that there's on-chain and off-chain code. On-chain code is the scripts we were discussing, the scripts from the UTXO model. So in addition to public key addresses, we have script addresses, and outputs can sit at such a script address. And if a transaction tries to consume such an output, the script is executed, and only if it succeeds, the transaction is valid. So how it works is if a node receives a new transaction, it validates it before accepting it into its mempool and eventually into a block. And for each input of the transaction, if that input happens to be a script address, the corresponding script is executed and must succeed. And if it doesn't succeed, then the transaction is invalid. So that's the so-called on-chain aspect of Plutus. And the programming language this script is expressed in, is written in, is called Plutus Core. But you never write Plutus Core by hand. Instead, you write Haskell, and then that gets compiled down to Plutus Core. And eventually, there may also very well be other high-level programming languages like maybe Solidity or C or Python that can compile down to Plutus Core. So that's the one thing. That's the scripts, and the task of a script is to say yes or no. Can this transaction consume the output I'm locking? Yes or no. But in order to actually use such an output that is locked at a script address, so in order to create a transaction that will unlock such an output and use it as input, you of course must be able to construct a transaction that will then pass validation. And that is the responsibility of the off-chain part of Plutus. So there is a part that runs in the wallet, not on the blockchain, and that will construct suitable transactions that are then able to unlock a given script output. So that's like a dual role of on-chain and off-chain. On-chain checks and validates. It doesn't do anything. It just says yes or no. And the off-chain part constructs, actively creates a transaction that will then pass validation. And the nice thing, or one of the nice things about Plutus, is that both the on-chain and the off-chain parts are written in Haskell. So one obvious advantage of that is that you don't have to learn two programming languages, just one, Haskell. And the other advantage is that you can share code between on-chain and off-chain part. Later in this course, we will talk about state machines. Then this aspect is even more direct. There you can really use the same, literally the same code, both for checking and for construction. But even if you don't use state machines, there's still a lot of possibility to share code. So if we briefly look at the code, so here, for example, this is just a Haskell data type that defines an auction. So it's the seller, the deadline, the minimum bid, and then the last two define the NFT and various other data types. And here, this is the heart of the on-chain code. So this defines the script, the logic of the script that validates whether a transaction is allowed to spend a given output sitting at this auction contract. So there are various helper functions here to do that. And so this is that. And then here, this is where the compilation happens. So this function I just showed you is just Haskell, but then here we use something called template Haskell to activate a GHC plugin that then compiles this Haskell code to Plutus Core. And here the off-chain part starts, which defines various parameters for endpoints that can be then invoked. So we have three endpoints for this example. Start will be used by the seller to start the auction, to lock the NFT into the auction contract. And then bid and close. So bid obviously will be used by bidders to make a bid, and close will be used either by the winner of the auction or by the seller. And so here these operations are defined. So this is the start logic. Then we have the bid logic here. Okay, it goes a bit further. And then finally here the close logic. And then some helper functions, and this just basically packages everything up. It says, okay, we will have these three endpoints, start, bid, and close, and they are called start, bid, and close. And the last lines are just for demo purposes or for trying it out in the playground to create a sample NFT that we can use to auction away. So that has nothing to do with the actual contract. And what I said about code reuse, for example, if we look here at the bid off-chain part, that uses a function min-bid here, with basically determines giving on the current datum on the state of the contract, whether there was already a bid or not, determines the minimal bid. And if we look for that, we see that this is defined here, and it's also used here. We are in the on-chain part. So obviously the script must check if a new bid comes in, whether it's high enough. So it's useful to have a function that computes the minimal bid. But also in the off-chain part, where I'm back to now, it's also useful if the wallet, before it even bothers constructing a transaction that makes a bid, checks whether the bid is high enough. That's not strictly speaking necessary. The wallet could just construct the transaction anyway, but then it would be doomed to fail. So it would be stupid to actually construct it in the first place. That's why I have this check in here that checks whether the bid is actually high enough. But the point I want to make is that this min-bid helper function can be shared between on-chain and off-chain code, because it's just a plain Haskell function and can be used in both parts of the Plutus contract. So that's a very nice aspect of Plutus, that you don't have code duplication between the on-chain part that lives on the blockchain and is responsible for validation, and the off-chain part that runs in the user's wallet on the user's local machine or later in the user's web browser, and is used to construct transactions that will then pass validation. So it's important to keep these two uses apart and to realize what they are. And sometimes it's confusing when people talk about smart contracts or contracts. What do they mean? Do they mean the script, the on-chain script, or do they mean the off-chain part that lives in the wallet and runs in the wallet? And it's even more confusing because the Haskell data type used for the off-chain part is also called contract. So if you talk about contract, do you mean this capital C contract, the off-chain contract that's executed on the user's machine, or do you talk about something else? So it's important to be precise about what we actually mean when we discuss something. Yes, but just to summarize, so we have on-chain and off-chain. On-chain gets compiled down to Pluto's core and is living on the blockchain and is executed by nodes that validate transactions. And we have the off-chain code that lives on the user's machine and is responsible for constructing transactions and submitting transactions that will then unlock certain script outputs. And both are written in Haskell, and that allows us to share code between them, which avoids code duplication. So we have a shorter code, and basically it's guaranteed that the parts fit together, or at least it's easier to make the parts fit together.